There, miss. You see, the heterodynes are feeding back into the stimulus reaction activators, causing non-synapse of the motor control resistor units.
Oh, that's good.
No, lady, that's bad. But your regenerative circuits are tuned asynchronously, and that causes concatenation in the intermediate amplifiers.
Well, that's bad, isn't it?
No, that's good. From now on, I don't think there'll be the slightest trouble with your robot. Your domestic problems are completely solved.
No one ever thought it was going to be easy, but building an intelligent robot remained the holy grail that challenged and tormented some of the greatest scientific minds for the latter half of this century. The advent of digital computers in the 1940s suggested the way forward. In America, ENIAC, the first supercomputer, was a giant brain composed of a room full of vacuum tubes. It was built in 1946 to calculate the trajectories of artillery shells. At the same time in Britain, mathematical genius Alan Turing was working on the Turing machine, a theoretical device used to process equations without human direction. The idea of mimicking human mental abilities through electronics was born.
His goal, as was the goal of all of the people who started in the field, was to achieve human-level intelligence. And he thought that computers would be able to play the imitation game, that is, would be able to successfully pretend to be human over a teletype line by the year 2000.
At a conference at Dartmouth College in 1956, Professor John McCarthy coined the term artificial intelligence, or AI. This conference inspired AI researchers at MIT, such as Marvin Minsky, to lay the groundwork for computerized thinking machines. They devised programs that could play chess, recognize different shapes, and solve logistical problems. Claude Shannon created a remarkable experiment called the mouse in the maze that appeared to learn. Driven by a motorized electric magnet, its path was recorded by a computer that remembered only the successful parts of the journey. On its second attempt, the mouse finds the target easily, in a fraction of the time. In 1963, McCarthy moved to Stanford University and established the Artificial Intelligence Laboratory.
One of the major things that we undertook to do was robotics, and in particular, computer vision in connection with robotics.
AI researchers figured that for programs to perform more like humans, they needed to be coupled with hardware to see, hear, and feel. Robot arms attached to TV cameras could perform very rudimentary tasks, such as moving colored blocks. But a dreadful paradox became apparent. While AI computer programs could easily outstrip human performance at calculus, when coupled with a mechanical appendage, they could barely achieve the hand-eye coordination of a toddler. Giving the basic sensory perceptions our brains accomplish effortlessly to robots was proving to be a Herculean task.
In hindsight, of course, it's obvious that those are actually the hard parts, because those are the things that human beings have done as a life or death matter for most of our evolution.
Yet while other labs struggled with these problems, Stanford Research Institute, or SRI, made history in 1969 by producing Shaky, the first ever reasoning robot that was mobile. Standing 5 feet tall, Shaky was driven by 2 motors and had a TV camera and radio link to an off-board computer. It could navigate, keeping track of its position and speed by counting wheel revolutions.
We wanted a system to be able to learn a little bit about its world, make a map, use that map to figure out how to make motion throughout its world, how to move.
Lacking a complex vision system, Shaky's world was a simply painted geometric environment, deliberately making it easier to perform the higher functions of learning and planning. Shaky could perform simple tasks such as moving a block from one place to another. From a general command, Shaky would assess the state of the world around it and deduce what it needed to do to complete the task.
And in fact, it worked very well. You could go in and move the boxes while the robot was performing some plan. It would recognize that things were going wrong. It would replan, and it would figure out what to do again. Just a phenomenal idea.
We put together a component in the area of computer vision, in the area of planning, and we put these together into a system that functioned smoothly, all as one integrated device. I think that was probably the first time that so many different components, so many different parts of artificial intelligence were put together into one system.
But even though Shaky's brain was impressive, spontaneity was not its strong point. Every move took more than an hour to compute, and even then, there was a high chance of failure. Over at Stanford University in the early 70s, they were having problems of a different nature with their robot vehicle, namely trying to keep it under control. The AI lab was experimenting with the famous Stanford cart, a mobile robot which, unlike Shaky, could see and navigate in any environment.
The cart had on it a television camera, and we illegally used an unused television channel, and we used model airplane type controller to get the information back to the cart.
From 1971 to 1979, AI students like Hans Moravec wrote programs which developed the cart from a dimly aware road hazard to a machine able to track its path from the horizontal shape of the skyline.
You could use it indoors or outdoors. You could move chairs and tables. No, you didn't need special kinds of objects. It could recognize just about anything. In fact, natural objects worked better with the cart.
The cart had one camera that took a series of 9 images from which it would gauge the distance to an object by using 9 separate coordinates. Its performance, however, still lacked perfection. On a good day in 1979, it could successfully cross a cluttered 30-meter space, but it took 5 hours to do so. The dreams of AI roboticists were constantly pulled back down to earth by the harsh reality of current technology. But upgrades in computer processing power did lead to progress. Flaky, son of Shaky, emerged at SRI in the late 70s. Roving SRI like a distant cousin of R2-D2, Flaky could interpret even vague statements from its master and perform an appropriate action.
I want Leslie to have the bagel. Enter.
I want Leslie to have the bagel. Finished successfully parsing sentence.
The master only said he wanted Leslie to have a bagel. Flaky reasoned he must find her and deliver it.
The idea at that point was that you were trying to make a robot that would essentially be a robotic person. That is, it would have all the capabilities, hopefully, eventually, of a person self-contained within this one box.
Flaky saw through a TV camera eye. Its sonar sensors were hooked up to a map-making program which plotted and stored information.
It's able to move in real time. It builds up its model of the world very quickly, say as it moves down the corridor. It figures out that it's in a corridor, that it hits an opening like a door, that it's supposed to turn in that door, and that it actually does turn into that doorway.
By the late 80s, Flaky was given stereoscopic vision and enhanced speech recognition software. but it was still a far cry from the goal of human-equivalent robots envisioned by the pioneers of AI at the dawn of the computer age.
Sign here.
Robot mining devices that operate on a track placed along the wall can mine 17 to 20 feet in an 8-hour day. There are only about 100 of these robots in the US, but they produce about 1/3 of the coal coming from underground mines. Modern Marvels will return in a moment. Marvels.
Tobor, the most amazing, the most fantastic creation of man's mind.
Oh, he looks alive.
Throughout the 1950s, 60s, and 70s, popular culture tenaciously held on to the vision of the intelligent robot. But fantasy still far outstripped reality. Mechanical men built during this period, like Swiss engineer Peter Steuer's robot, were little more than sophisticated automatons, close cousins of Electro and Sparko from earlier decades. However, researchers were pursuing the dream of a human-like robot, one arm at a time. In the 1950s, highly dexterous mechanical arms had been developed for handling radioactive isotopes. SAM was built for NASA to operate in radioactive test sites and in outer space. But these machines were teleoperated, reacting only to human control. Then scientists at Stanford and MIT coupled this mechanical dexterity with the new advances in artificial intelligence and vision systems. Experimental robots like the Salisbury Hand gave the machines a refined sense of touch, so they could handle small and delicate items. In the early 1970s, several Stanford graduates recognized the potential of these breakthroughs for private industry and formed a company to manufacture and market these intelligent robot arms.
That company had 3 people, Vic Scheinman, myself, and Bruce Shimano. The company was called Vicarm, which stood for Vic's arm, and we began to build small electric computer-controlled robots for research purposes.
The Vicarm could move with unprecedented precision and reliability. It was capable of repeating a motion with stunning accuracy. The partners wanted to take their invention to the industrial market, essentially giving the Unimate a brain. So like Joe Engelberger before him, Vic Scheinman took his robotics show on the road. Ironically, it was Engelberger who got him in the door, literally at a trade show in Chicago in 1975.
All of a sudden there was this commotion out on the steps, and we asked security to go out there and see what was going on. Well, Vic Scheinman was out there with a briefcase. He'd open up his briefcase and this little robot arm would move around. So we threw him out of the trade show 2 or 3 times.
And he was standing out in front of the show with a robot under his arm, and it was like a Frenchman selling filthy pictures, you know. And I said, come on in, Vic, and we'll put a table up at the corner of our booth and you can start showing people. And all the attention came to Vic's little arm.
Unimation was so impressed that they bought the Vicarm company. General Motors then commissioned them to create a new robot for automobile assembly lines. Together they developed a robot that set an industry standard, the Puma, Programmable Universal Machine for Assembly.
The Puma was an industrial version of the Vicarm technology. It had incorporated into its base an LSI-11 computer, a small microcomputer. It could move to a repeatability of 0.004 of an inch, which is about the thickness of a sheet of paper. That early computer had only 8 kilobytes of memory in it. And I remember my partner, Bruce Shimano, commenting to me that he didn't think he'd ever be able to develop enough software to fill 8 kilobytes of memory.
Unlike the massive hydraulically controlled Unimate, the Puma was a small electric robot.
The movement to an electric motor to help drive the robots really was a key point, and that was a benchmark time, and it created a lot of new application interest areas and expanded the industry quite dramatically, going from hydraulics to electric.
Originally, the Puma was sized to be about the same size as a person, and the idea was that it would be very difficult to get the workforce and the plants to accept this kind of technology, and if it was sized about the size of a human, you could imagine using some places where robots would perform the work or other places where people could perform the work, and if there were problems, you could backfill that technology with people.
Puma sales quickly grew to about $35 million a year, and a thriving industry in intelligent industrial robots was born. Soon, the vision systems were improved so robots could recognize and manipulate parts randomly placed on a moving conveyor belt. The robots were taught this remarkable task by first showing the parts to the machine's video camera eye. The computer would memorize that shape and look for a match as parts came down the conveyor belt. By now, robots had achieved intelligence roughly equivalent to that of a cricket.
One application in the mid-'80s was in the food industry, where robots were picking up candy that was coming down a moving conveyor belt, or cookies that were coming down a moving conveyor belt, using machine vision to find the candy or the cookie, then picking it up and putting it into an appropriate package.
During this time, General Motors bought about half the industrial robots manufactured in the U.S. and decided to form its own robotic division. Westinghouse also got into the game by buying Unimation. Carlyle and Shimano, not keen on becoming conventional corporate types, formed their own company called Adept. Adept specialized in improved machine vision, and they incorporated a new mechanical technology called the direct drive robot arm. Older robot arms had large motors located in the base of the machine and systems of wires, pulleys, and gears to control the joints. The play in these arms prevented them from performing precise movements. But the direct drive arm placed small but powerful electric motors at every joint on the arm. Motors that generate tremendous torque. Originally developed at Carnegie Mellon University by Takeo Kanade, direct drive arms generated an immense leap in speed, reliability, and precision. Movement repeatability was reduced to about 1/3 the thickness of a sheet of paper. Today, Adept is one of the few successful American industrial robot companies. GM and Westinghouse have both dropped out, and the industry is dominated by companies from Japan, where the robot market is 5 times larger than in America. Japanese companies such as Fanuc Robotics have branches throughout the world. And although these companies didn't invent industrial robots, they have added new levels of efficiency to the technology.
They saw something good. They don't worry about whether it was invented there or not. They figure out how to use it most effectively for their objectives. Their most recent motor factory has 200 robots and 40 operators in the plant, and is capable of running overnight, unmanned, actually for a full 3 to 4 day weekend.
At Fanuc's headquarters, they even have robots building other robots. The Japanese have honed the once awkward robot arm into a dexterous tool eerily similar to a human limb. They proudly display the capabilities of their robots in impressive demonstrations. Robots balancing spinning tops on the edge of a sword. Or coordinating 2 arms in a demonstration of flower arranging. Or agile robot fingers manipulating a tiny bolt. And even a robot arm that uses its vision system to draw remarkably accurate portraits. The beret is optional. The next challenge was to move robots from the factory floor to the outside world.
Director, playboy, recluse. Now take a look at his invention. We now return to robots on Modern Marvels.
By the late 70s, robots had become fixtures in laboratories and on factory floors. But these were controlled environments, and it was unclear when robots would take on the challenges of the real world. At Carnegie Mellon University in Pittsburgh, scientists tackled the highly complex problems of programming robots to sense, plan, and think in the natural world. The majority of funding for robots went toward basic research aimed at solving theoretical problems. But that was all about to change. In a small farming community less than 200 miles from Carnegie Mellon, the core of reactor number 2, the 3 Mile Island nuclear facility, suffered a near catastrophic meltdown. To avert a disaster, the operators were forced to flood the reactor's basement with 600,000 gallons of water. The contaminated sludge, along with unknown levels of radioactivity, made any human exploration potentially deadly. 3 Mile Island turned to Carnegie Mellon for help, and the industry of field robotics was born.
3 Mile Island was a galvanizing event in our personal history. It was the opportunity to take machines full term, not just ideas and laboratory curiosities, but full up working machines that would go into that accident and perform serious work.
The first robot to enter the disaster area was the Remote Reconnaissance Vehicle, or RRV. The 6-wheeled robot carried 2 onboard cameras, radiation and infrared sensors, and an array of photographic equipment. The RRV was made stable enough so that it would not tip over into the toxic cesspool, and small enough so that it could fit through existing doorways in the reactor's core. Then, in November of 1984, the RRV made the dangerous plunge into the 3 Mile Island hot zone.
When the reconnaissance vehicle went into the containment building for the first time, was high drama. We were able to view the surroundings, the conditions, the flooding, the damage. But more importantly, an event frozen in time where lunchboxes and watches and ladders were just abandoned as people left. And it was truly special, since this machine was the first thing to have gone in, and to this day, the only thing to have gone into the basement.
The scientists knew that one of the most important things about sending a robot in was the ability to get the robot back out. Otherwise, they had just added several tons of new nuclear waste to the problem. For this reason, the RRV was able to negotiate its way back to a lift station, dock itself to a hook, and be hoisted into a washdown area above the toxic sludge. A heavy gauge tether was also added to allow for constant communication and, if necessary, to function as an escape plan of last resort. A 10,000-pound giant known as Workhorse came next. It was built to disassemble the contaminated areas. The powerful robot had the ability to grasp, saw, and extend to heights of up to 30 feet. Though it was never deployed into 3 Mile Island, it was part of what Whitaker realized was an emerging market for his field robots, performing jobs that were too dangerous for humans.
In the earliest going, before the existence of field robots, there were no research contracts. We created opportunities from hazard and operated as technical ambulance chasers.
A new industry had been born. But these machines looked and acted nothing like the popular conceptions of friendly humanoid robots.
A friend of mine came to visit, and I took her on a tour, and she walked around and she said, well, nothing has a head. She really wanted to see a face and arms and the whole bit on the robotics, and was kind of surprised when they look like trucks and they look like tractors and they look like Jeeps. I think there's a certain artistic movement in robotics to build some human-like robotics, and certainly the ultimate in robotics would be duplicating a human. In our work, that's not necessary. We think humans can do good human things, and our machines are designed to assist rather than replace the human individual.
In 1988, Whitaker co-founded a company called Red Zone to build robots for dangerous jobs. Red Zone designers shape the robots for specific tasks, and the machines often take strange and unusual forms. Fury slithers inside underground storage chambers and uses powerful magnetic wheels to attach itself to the tank walls.
It was intended for tank inspection, so that it could go in and actually inspect the inside of a tank without having to empty the tank. So that if a tank had fluid or liquid in it, it could actually be dropped in and inspect for cracks, leaks, that type of thing.
Houdini was created for cleaning radioactive sludge out of nuclear waste chambers. Like its namesake, Houdini can crawl into places other robots can't.
For robots that will work inside tanks, inside pipes, inside mines and caves, there are two approaches. One is to forcefully make openings large enough to enter. The other is to collapse, become small enough to go through existing openings.
This particular robot folds like a parallelogram, so it can go down a 22-inch diameter opening. And that's typical of the kind of openings that were left in a lot of these nuclear waste tanks. So as the bulldozer folds, it goes down in the tank, opens back up, and then it can move waste around in the tank to the clean out sumps and so forth.
Today, a new generation of the Houdini robot, called Pioneer, is being developed and tested at Red Zone for use at the Chernobyl nuclear accident in the Ukraine. The radiation levels at Chernobyl were so massive that over 30 of the first humans to investigate it died within weeks or months. Researchers learned quickly that if they weren't careful, extreme radiation could spell death for robots too. By melting electronic wiring, fogging camera lenses, and destroying rubber treads. Most field robots rely on wheels and tracks to navigate through perilous terrain. But many jobs require another, more complex system of locomotion.
Perhaps a third of this world, and maybe much more of other planets, is inaccessible to the traditional locomotors like wheels and tracks. Legs, as manifested in nature, show incredible ability to climb and maneuver, to scale near vertical walls. And this motion can theoretically be done with efficiency beyond that achievable with wheels and tracks.
Early experiments with legged movement, like General Electric's walking truck, known as the Elephant, found few uses and were incredibly expensive. In the early 1980s, Ivan Sutherland built his walker. The position of the 6 legs were controlled with microprocessors, while an 18-horsepower engine propelled the robot at about 2 miles per hour. Sutherland's design gathered valuable knowledge about balance and coordination. Although the attempt was interesting, it was not very practical. The answer to many of the problems facing walking robots came from California's Odetics Corporation and their Odex-1 Functionoid. It could navigate relatively flat surfaces with ease. It also had amazing balance, climbing ability, and strength, able to lift several tons using its entire body, or up to 450 pounds with a single leg. But independent thought and outdoor navigation still eluded even this impressive robot. Ambler was created at Carnegie Mellon to be fully autonomous and take on tough terrain like large boulders and deep crevices. Unlike animals or insects, Ambler could move any of its 6 legs independently. The robot's vision and reasoning systems allowed it to plan leg placements up to 1,000 moves ahead, as if playing a masterful game of chess.
The first couple of times we moved it, it was pretty scary. It's almost like a building next to you is getting ready to shift. Almost all of these things, when you first start them up, you don't know what they're going to do, so you sort of put them in a condition where they're not going to hurt anybody, and you stand back.
But this much thought required a massive superstructure weighing thousands of pounds.
Ambler was self-contained, self-reliant with everything on board. Once the sensing came on board, once the computers came on board, there was a need for power. That increased the mass, that increased the scale, and this was a problem that spiraled, feeding itself, and the scale of Ambler is a result.
Ambler had been intended to explore Mars, but its monstrous size made that trip impossible. Instead, Red Whittaker's team had to find new, dangerous territory on Earth for Ambler's descendants. The scientists chose the Mount Erebus volcano in Antarctica. The robot to explore this uncharted hellhole was an 8-legged walker known as Dante. The robot went through rigorous testing on the slag heap of an abandoned Pittsburgh steel mill before making the 13,000-mile trip to the White Continent.
We deployed Dante onto the volcano in thousands of little pieces and parts with 250,000 lines of fresh software, new sensors, new physical form. In tents at 10,000 feet, we assembled it piece by piece, downloaded software, brought it to life. I was amazed this thing walked.
In the end, it was ice rather than fire that killed Dante. Wiring and circuitry intended to withstand the extreme heat of an active volcano was unable to survive the severe cold at the top of the mountain. And Dante failed after only 3 steps. The makers of Dante went back to the drawing board and redesigned their creation. New leg configurations, joint placements, and metals made Dante 2's legs 3 times as strong as its predecessor. Dante 2 was sent into Mount Spur, an Alaskan volcano. Step by step, it negotiated loose terrain and withstood a barrage of falling rocks as it made its unprecedented descent. Dante's sensors allowed researchers to take seismic readings, view video images, and even smell the chemical content of the air, all from their command post in Anchorage, over 200 miles away. Eventually, the extreme terrain and high winds combined to tip over Dante 2, and the robot had to be airlifted to safety. Red Whittaker and his field robots team have helped build an industry for robots that step in when our own technology backfires. They've gone into nuclear reactors and noxious volcanoes. But other scientists are dealing with a subject even more daunting: rush hour traffic.
Now this
on Modern Marvel's Boys Toys Week tonight. We now return to robots on Modern Marvels.
Like an infant learning to walk, robots had taken their first awkward steps. But like a teenager learning to drive, true freedom would only come once robots could travel great distances on their own. In 1979, Hans Moravec brought the knowledge from his Stanford cart to Pittsburgh and joined forces with a team from Carnegie Mellon University to create mobile robots. Carnegie Mellon researchers had been working on their own cart called the Intelligent Mobile Platform, or IMP. This hallway navigator borrowed autofocus sonar technology from Polaroid cameras to map its world. It scanned its environment as a lighthouse would, but sonar proved to have severe limitations.
It can't see very far away. It has a problem if you have a smooth surface, the sonar just hits the smooth surface and bounces and never comes back. And so you may think that there's nothing there when in fact there's a nice smooth wall.
Moravec's next project with the Carnegie Mellon team, called Uranus, used specially designed wheels to overcome some troublesome technical issues.
Uranus exhibits that unique ability to move instantaneously in all directions, not just like we drive a car, but also to move laterally, spin on a dime, or to pirouette so it could turn while moving. And we couldn't solve the parallel parking problem, so we made machines that could move like chess pieces that could execute the kind of simple plans and models that we could create.
With the advent of microcomputers in the mid-1980s, scientists dreamed of finally creating a fully autonomous mobile robot. But even using state-of-the-art technology, they required a specially rigged truck dubbed the NavLab 1. The robot vehicle needed a separate 4-cylinder engine to power 4 computer workstations, a supercomputer, its vision systems, and an air conditioner. Graduate students sat in the back to control the equipment, but the big truck was driving on its own. Originally, few people believed that NavLab would ever travel over 5 miles an hour and then be able to stop.
The NavLab 1 typically ran at about a walking speed. In fact, my son was born at the same time that we built the NavLab 1, and we had a contest that when he was crawling, it was moving at a crawling speed. When he learned how to walk, it was moving at a walking speed. When he learned how to run, it was moving at about a running speed. He finally got a bicycle, and then the NavLab 1 was moving at about the speed he could ride his bicycle.
NavLab ultimately exceeded 20 miles per hour, but children on bicycles were just the kind of object that its vision system had difficulty handling. NavLab was equipped with stereo video cameras and a laser rangefinder, but it still had great difficulty telling the difference between changes in terrain. The blue truck was replaced with NavLab 2, a U.S. Army Humvee fitted with an impressive new vision system known as Alvin. Alvin is what is called a neural network program. It's actually capable of learning to drive. Alvin is shown the road through a video camera while a person does the driving. After about 5 minutes of this learning process, Alvin takes over and continues driving on its own. NavLab 2 eventually reached driving speeds of 55 miles per hour. Then, in 1995, the NavLab team decided to try a new streamlined approach with their robot vehicles.
We said, look, rather than putting all the processing power and all the electrical power on board that we think we might possibly need, let's go the other direction. Let's figure out how much power is available just through the cigarette lighter. And let's limit our processing to whatever we can get off of the vehicle as unmodified.
NavLab 5 was a stock minivan, complete with laptop computer and multiple television cameras for front, side, and rear vision. Alvin was replaced by a more sophisticated neural net system, Ralph, which could handle lane changes and heavier traffic. In 1996, Thorpe and his students sent NavLab 5 on the No Hands Across America drive. in which it made its way from Washington, D.C. to California. Ralph did the driving during 98.2% of the trip. The newest nav labs have reached a point where the distinctions between robot and car have all but disappeared. The computers, radar, and cameras are now virtually undetectable. And that, Chuck Thorpe believes, is the whole point.
Oh, if you take it to show it to my son's 6th grade class, they're disappointed because it doesn't look so impressive. But that's really the idea, that computers are disappearing, the robotic stuff is disappearing. It's more and more of a comfortable environment that just feels like a car, a very smart car that can help you drive, but very much a familiar environment to be driving.
The same technology that drives NavLab has also been employed by other industries, such as earth-moving and farming. Some tractors can now distinguish between cut and uncut crops and plow entire fields without an operator. And one day soon, unmanned helicopters will be able to perform search and rescue missions more efficiently than humans ever could. But the ultimate goal of the NavLab project was not just exploration of our own atmosphere. A planetary rover called Nomad also used the technology. The Chilean Atacama Desert, the driest on Earth, was chosen to test the new robot because of its resemblance to the Martian surface. Nomad was designed to operate autonomously for long periods, navigate through unfamiliar territory, and identify meteorites and other rock samples. The robot vehicle plotted its own course for the majority of its 6 weeks in the desert. When it was given directions, they often came from classrooms halfway around the world that were set up to communicate with the robot. Nomad was intended to operate in much the same way as NASA's Pathfinder, designed by the Jet Propulsion Laboratory. Pathfinder sent back startling images from the Red Planet and spawned a new generation's interest in space exploration and robots.
The application of robotics in medicine is a rapidly evolving area. Work has been done on robotic diagnosis and robotic radio and laser therapy. Modern Marvels will continue in a moment. Carmen Electra hosts Howard Hughes Tech on Modern Marvels Boys Toys Week tonight.
Now on home video from the History Channel. Own your copy of this program delivered directly to you for just $29.95 plus shipping and handling. To order, call 1-800-708-1776 or shop historychannel.com.
Tech Thursday is brought to you in part by Fox Home Video.
This Tuesday, a murder only he can solve.
My robot. And Lipitor has proven benefits for your heart. Lipitor is not for everyone, including people with liver problems and women who are nursing, pregnant, or may become pregnant. Simple blood tests are needed to check for liver problems. Tell your doctor about other medications you are taking, or if you experience muscle pain or weakness, as they may be a sign of a serious side effect. So take the next step. Ask your doctor about the benefits of Lipitor.
It's not your job.
It's not your laugh. It's not your hair.
It's not your shoes. It's not your car.
You can tell more about a person by the watch they wear than anything else. Seiko Kinetic, powered by the movement of your body.
It's your watch. Some people believe there's a carpentry gene, and I think I got it. Hanging things, I'm a little hit or miss on. But with the Black & Decker Bullseye, it's foolproof. I just find a stud, hang it on the wall, and it self-levels. Gives you a straight line every time.
The Bullseye from Black & Decker.
My dog thinks I'm Elvis.
Howie, Sirius Satellite Radio with greatness.
Yeah,
We got all these different channels. Country, rock, even your favorite, rap. Sirius digital quality sound coming through.
Just like me in the playoffs.
Hurry into Radio Shack now and save $50 on Sirius Satellite Radio after rebates when you buy a receiver and home or car docking station and subscribe to 3 months of service.
I could use a commercial break right now.
Sirius Satellite Radio at Radio Shack.
Thank you very much.
Start cleaning with HGTV's Mission Organization. It's packed with practical advice to get you organized.
Wow, you did all this today?
So clear out the clutter, label the litter, break out the garbage bags, and throw stuff out.
It was either the garage or Bob.
Mission Organization, Wednesday nights at 9:30 on HGTV.
Let Closet Factory, your custom storage solution authority, help you clear the clutter. Call Closet Factory at 1-800-667-3496 for your free design consultation.
The all-new Jeep Grand Cherokee. With Quadra-Drive 2, our most advanced four-wheel drive system ever, a 5.7-liter Hemi V8, and our new electronic stability program. The off-road legend continues on-road. Now, during the Jeep year-end sales drive, get a combined cash allowance of $2,000 on Grand Cherokee. Hurry, ends January 3rd.
Is a boy's toy.
Great, let's shoot this. Action.
Yeah. Awesome! Vroom.
Modern Marvel's Boys Toys Week with host Carmen Electra. All this week on the History Channel. We now return to robots on Modern Marvels.
The evolution of robots has transformed them from primitive experiments into remarkably capable machines. Today, even a child's robotic toy possesses more power and functionality than the most advanced robot of 50 years ago. But as impressive as they've become, one element is still clearly lacking. Most successful robots don't look anything like the robots of our fantasies. Whatever became of our original vision stated so many centuries ago? To create a machine in our own image, to be our dutiful servant. In the early 1980s, Nolan Bushnell, founder of Atari and inventor of the first video games, founded Androbot, a company dedicated to putting an intelligent robot in every home. The basic Androbot model was named Topo. This robot was designed to be remotely controlled by your personal computer. Topo was programmed to sing, dance, and deliver witticisms, but it wouldn't know where to start dusting the furniture. In fact, it was unable to distinguish its master from the furniture. However, the top-of-the-line Androbot was endowed with far more intelligence and autonomy. It was known as Bob.
Hi, folks. Bob was the Cadillac, the starship. This was meant to be the be-all and end-all robot. Brains on board is what it stood for. It had multiple processors, a cool operating system, and censored to the hilt.
Bob was completely self-contained. It was equipped with dual reprogrammable computers, infrared sensors to detect and recognize human beings, ultrasonic sensors to navigate through the house, as well as speech and voice recognition.
Your humble servant.
Bob, get me a beer.
What Bob would do would be a somewhat more amusing companion than a dog or a cat. Then you can go into what I'd call basic fetch activities. Bring me a Coke, bring me my newspaper, bring me my slippers, that sort of thing.
Prices for Androbot robots range from about $700 to $2,000. Despite glowing early projections, lack of funding and the limitations of 1980s technology forced Androbot out of business. However, today Joe Engelberger has re-emerged on the scene with a new service robot known as Helpmate, which is now being tested in hospitals. The Helpmate delivers meals and medicines in more than a dozen U.S. hospitals, allowing personnel to spend more time with patients. The Helpmate has learned to negotiate its way through the use of an array of infrared sensors. It can even call elevators.
Please stand clear.
And knows when it's time to recharge.
My battery is low.
Please call the operator. I am about to move.
Engelberger also manufactures the aptly named Scrubmate. Engelberger sees a bright future for service robots, which he appropriately quantifies in automotive terms.
Certainly in less than 50 years, there'll be household robots just as likely as Cadillacs. Probably not as likely as Chevrolets.
These personal service robots rely on artificial intelligence, but also artificial personality. They are not required to look exactly like a human being.
Do you want it to have personality, or do you want it to vacuum the floor? If it's a function bot, humanoid is less important. If it's a entertainment bot or a pet bot or some of those things, it has to be cute. It doesn't necessarily need to be anthropomorphic, but it needs to be cute.
In the entertainment industry, it is critical for robots to look as lifelike as possible. Companies like AVG in California create lifelike replicas of man and beast for amusement parks and museums around the world. Creatures from dragons to dinosaurs achieve an alarmingly high level of realism. But in order to sell the illusion, designers go to great lengths to replicate human form and action. Skin is created using specially formulated silicone rubber. A key step is to carefully synchronize the pre-recorded voice to the robot.
I think I know now what they mean by the expression, if looks could kill.
You actually synchronize the soundtrack with the computer. They slave each other, so they always work together. And then you start putting layers on top. You start maybe with the mouth, synchronizing the mouth to the soundtrack. Then you start adding facial expressions, blinking. Then you start adding the head turn and the eyes. You always have to make sure that the eyes are leading the head. Otherwise, it will look really robotic. To make something believe, you got to make sure that all the movements have the right sequence to look alive.
Most of these robots are powered with pneumatics, air pressure. Others use hydraulics. Oil running through hydraulic lines creates fluid movement, but can quickly destroy the illusion.
Hydraulics is the best quality movement, but it has maintenance problems where if you lose a hydraulic line, you ruin thousands of dollars in cosmetics treatment because the oil starts leaking all over the place, and sometimes it looks very gross.
Sarcos Entertainment in Utah also builds lifelike creatures for theme parks and museums. Their Sarco Man achieves his remarkably realistic movement through teleoperation or can be computer controlled. But despite their appearance, most entertainment robots are not very smart. They're really just highly sophisticated automatons. But what if their realistic features were combined with advanced artificial intelligence and dexterous industrial robot arms and mobile field robotic legs? How possible is the creation of an android, a true artificial human being?
The comparisons are always very, very difficult. I mean, we know what the robot's supposed to be. It's supposed to be me. And so very few new technologies have that comparison problem. Usually a prototype is the first of its kind forever, and so it's as good as it gets. Wow, that's neat. Whereas the robot, compared to the human being, is always lacking.
One of the most advanced attempts is the Honda Human, a top-secret 10-year project that put brains in an amazingly realistic body. It does things that until recently the most ambitious roboticists thought impossible. Not only can it move upright on 2 legs, it can also negotiate a set of stairs on its own. It sees through 2 eyes inside the helmet and carries its brains and battery on its back. In another decade, Honda intends to bring its human out onto the factory floor to work alongside human beings who will control it by simple voice commands. While Japan leads the way in building robot bodies, the Artificial Intelligence Lab at MIT is making serious headway in building smarter brains. Here, they built Cog, a humanoid robot who is the logical heir to the cybernetic tradition of the 1950s. A robot designed to learn through its interaction with humans in the world.
In order to act intelligently, there's a lot of things you have to know about the world. And one approach is to try and tell an artificial intelligence program everything, write it out in great detail and tell it all the facts. By building a robot, we're trying to build a system which can act in the world, interact with people, and learn for itself. And our hope is that that will lead to a quicker accumulation of the sort of knowledge of what it is to act in the world so that we can have true artificial intelligence.
Cog is its own laboratory of machine learning. Like a child, it builds up knowledge by experience and experimentation, eventually, in the distant future, developing adult intelligence. Cog looks human because Brooks believes that to gain human intelligence, a robot must experience the world in a similar physical way.
A lot of us have seen Star Trek, The Next Generation with Commander Data, the android robot, which is very human-like, except he doesn't quite have emotions. That's our ultimate goal. We're trying to figure out how to build a robot that is that capable. It's going to take a long, long time. It may take longer than 400 years. This is some of the first steps towards that goal.
Basing his predictions on the exponential increase in computer processing power, which doubles every 18 months, Hans Moravec believes robots will make a great revolutionary step every 10 years. First, they will achieve the intelligence of a lizard, then a mouse, then a monkey.
And the fourth generation robot is human-like, and expect those perhaps around 2040. At that point, we're pretty much out of work because the robots can do everything we can do better and cheaper.
Undoubtedly, we will someday fulfill the science fiction vision of intelligent humanoid robots, whether it be in 40 years or 400. But as fantasy and reality merge, one question remains unanswered. Who will be calling the shots? Will it be us, or will it be the robots?
So what you're going to do is you're going to rev the engine like this.
I think the throttle's over here, and it goes like this. Vroom, vroom. Kind of like that.
Modern Marvel's Boys Toys Week with host Carmen Electra, all this week on the History Channel.
Creatures appear to respond like simple animals and learn just by reacting to a variety of basic stimuli, such as light. Independently of Wiener, British neurophysiologist Gray Walter created the famous cybernetic turtles in the late 1940s. These robots experienced the world with phototubes, microphones, and contact switches, and could navigate through the environment. One of the most impressive of all cybernetic animals was known as the Beast. It was built in the early 60s at Johns Hopkins University's Applied Physics Lab.
The environment in which this vehicle is to live is that of the halls of the Applied Physics Laboratory. There it must cope with the various obstructions around the wall while seeking out sufficient power outlets from which to keep the battery charged, which are located in the lower part of the body section.
The Beast's goal was continuous motion and unassisted survival in this environment. Equipped with sonar, a photocell eye, and tactile sensors, it managed very well.
During the working day, most office doors are left open. It is desirable not to allow the device to enter these offices and must, therefore, sense the door jamb, bridge the open door, and regain acquisition with the wall.
It could even prevent itself from falling down stairwells. When trapped, it went into a vibratory mode to shake itself free. The beast had no real brain, just sensors, but its electronic behavior patterns allowed it to survive in the world. This bottom-up approach of achieving the bare rudiments of intelligence with simple models of animals was soon eclipsed in the early 1960s as a new field took hold: artificial intelligence.
Now this is a boy's toy.
Great, let's shoot this. Action.
Awesome!